I think we should go to 4-day work weeks.
Yes.
So like Friday or one day would be, decompress. Another day is like fun stuff, and then one day is to get your life together. So we're looking at 1-2. We will finish 1-2 today. That's the goal, which means 1-2 homework will be due tomorrow. Now, 1-1 homework. Y'all need to help me remember this. When I finish the notes on something on a Friday, if you'll help me remember to set the due date for like Saturday, because I know that we got football players, we've got dance, we got cheerleaders, we got band, and I know on Fridays, like your day is shot in terms of trying to do schoolwork, except for flex, but that's before you get to me anyways. So I'm going to go back to the 1-1 due date and extend it to Saturday over the weekend to Saturday. So that way, if any of you worked on it Saturday, it's going to give you full credit, because I know that I started thinking about y'all's commitments on Friday and how they go into like midnight. But so if we finish notes on a Friday, help me remember to set that due date longer ahead of time. All right. 1-2 notes. We were looking at functions and graphs, and we got to a stopping point right here. We were evaluating functions by plugging in the values, and then we got fancy with it. Instead of plugging in integers, we were plugging in polynomial expressions and having to do the algebra 2 with cleaning it up. And that's where we left off. Moving to this slide right here. Graph functions. This function is f of x. Notice it says x squared minus 5. You can look at graphing functions in multiple ways. This is, do you remember the vocab word to describe what type of graph this will be?
Parabola.
It's a parabola. Starts with a Q. Quadratic. It is a quadratic function that will produce a parabola when you put it on the graph. There are multiple ways to graph quadratics. One of the ways to graph a quadratic is using what's called vertex form. Another way to graph a quadratic is the good old-fashioned T-chart. We are going to get to vertex form. Let's see. I can show you both. I'll show you the T-chart and I can show you vertex form. You should remember that from Algebra 2. If you ever need to graph something, and let's say you're just having a brain lapse and you don't remember what to do, good old-fashioned T-chart works every time. Now, because it's a quadratic, you do want to be picky with where you plug numbers in, because a quadratic either does this or this, correct? Okay, so if I'm picking numbers that are like out here, am I actually going to see where the curve is? No. So when you're graphing quadratics, if you pick numbers based on like just a T-chart, it would be helpful to know where the vertex is. This brings us to that vertex form from Algebra 2, or you can also go to your graphing calculator and you can enter it in y equals and then look at the table. So let me pull my calculator up. We're going to graph x squared minus 5. If you remember from Algebra 2 transformations, this is the parent graph for a quadratic, which is x squared. That's the parent graph. I call it the mother function. This is the parent. It's the mother function. And it's just shifting down 5, if that makes sense. So I've copied the quadratic into y equals. I'm going to hit zoom 6 and tell it to give me just a standard viewing window. And now I can see that it's all the activity is right here. That's where the curve is. That's what I want to capture on my paper. So let's pick numbers that are right around here and plug them in, or we can go to the table feature. So you've got to be able to read it. This x coordinate is 0. So if I plug 0 in here, I get what? I get -5. That was 0, -5. It's right there. Now I'm going to plug 1 into the quadratic. I can see that it's going to land here, right? I'm going to go to my graph, my equation, plug 1 in. What do you get? -4. You see how I got that? Now I'm going to plug 2 in. What do I get? -1. I'm going to graph those. I've got 0, -5, 1, -4, 2, -1. And I can see that I have half the curve. How do you get the other half? You reflect it over. When we get deeper into quadratics, we're going to learn that this is the axis of symmetry, or the line of reflection. And what happens is, if you graph a quadratic, if you graph half of it, then reflect it over, you have the other half as well. How do you reflect it? You just count. So this is 1 away, so 1 over, and you put the point. This is 2 away, so 2 over, and you put the point. Question, do I reflect the 0, -5 point? No, because the axis of symmetry is passing through it, which means it's the vertex, which means it doesn't, there's not another one. It doesn't reflect. It is the either lowest point on the graph or the highest point on the graph. So taking notes, we graphed it in our calculator, we looked at the graph, and then we picked x values near where all the activity is and plugged them in. Plug numbers in for x, and then you get, I'm going to draw an arrow to say, to get your value for y, graph, and reflect. Another nice thing about the graphing calculator is when you plug that equation into y equals, you can hit second table, and there is a running t-chart right there. That's an ongoing t-chart all the way. Now you do have to remember when you're reading the graph to read the numbers where the activity is. Find the vertex and then read that x coordinate, and that's absolutely what you need on your graph. All right, let's do the next one, which is starts with a C. Cubic. This is a cubic function. Let's just make a t-chart. Now the mother function for cubics is just y equals x cubed. To do cubed 2 ways, you can hit the math button and then it's option 3, or you can hit this little button. It's called the hat. I call it like the rooftop. It looks like a rooftop button, or a carrot. Hat sounds good. Carrot button, and then it'll, whatever number, like when you push the carrot button, it'll superscript and put it in exponent form. Now that's the mother function. Ours has -x after it, which means it's been tweaked a little. And then we're going to hit zoom 6. I want you to get comfortable with these graphs, being able to type it in, find the graph, zoom 6, get to the table. You can see the curve. It's a little crowded right here. What could I push in order to get a better picture?
Zoom.
Zoom in, right? Hit zoom, choose in. It's going to flash saying, okay, where do you want to center this zoom that we're about to do? I'm going to leave it right there. and then it'll zoom in, and that's a lot nicer. Now I can clearly see I want to go to my table, and I want to use numbers, say, between -2 to +2, because then I get that activity, right? So I'm going to go here, type -2, I'm going to write -2 to +2. I could evaluate that in my head, I could evaluate it in a calculator, or I could just let the calculator's table show me the values. Go back to the calculator, hit second table, and now I can arrow up so I can see what -2 was. Now I'm going to copy -6,0,0,0,6 to my paper. And now I'll graph them. And this is where being able to see, like, if you just went straight to picking numbers and putting it on paper, you might not really know how to connect those dots. You might sit here and start like, you might mess up or something. So that's why it's helpful to have the calculator, because then you saw the picture. The picture looks like that, and I know when I go to connect my points now how to try to recreate that curve. So when you have something like that, I usually try and do the most challenging part first, and then I go and fill in the end behavior where the graph is shooting off to. Going to the next slide, we've got the function, the square root of x plus 4. We're going to graph it. Go to your calculator, go to y equals. We're going to type the square root of x plus 4. The mother function here is the square root of x, and then it's been shifted 4 units. Looks like it would be to the right because it says plus, but it's actually to the left, because anytime it's a right or left movement, there's a sign change. It's counterintuitive. So this is going to be the parent graph for a square root function shifted left 4. Looking at the table, here's what it looks like. And I'm arrowing up on purpose. What? Yes. So what do you notice about the table? It's got error in it. And if I was to keep scrolling up, would it continue to say error? Yes. So my question to you is, why is there an error on numbers less than -4?
Because you can't grab an imaginary number.
There you go. So everything we're dealing with is real numbers, right? Might be ugly, might be real ugly, decimals, square roots, but everything we're dealing with are positive numbers under a square root, because we can't take the square root of a negative, it crosses into imaginary. Can't graph imaginary on the coordinate plane of real numbers. So the reason that anything less than -4 generates an error is because if you think about it, let's plug in -5. If I plug -5 in there, I get -1, right? And I cannot take the square root of a -1 because that's imaginary. Now if I plug -4 in, what do I get? I get 0. What's the square root of 0? 0. That's allowed, right? And if I plug in -3, I'd get 1, what's the square root of 1? 1. So you can see that there is a domain restriction. There's a domain restriction. So this is kind of tying back to what we covered in the Algebra 2 review. There is a domain restriction here. And basically, you cannot plug in any number less than -4. X, so in order to write this, we don't want to say X cannot be less than -4. We want to say what's allowed to be plugged in, because that's the positive angle. What's allowed to be plugged in? We can plug -4 in, right? But then you got to count what direction? Up or greater than. So the domain restriction here is that you can plug any number in you want as long as it's -4 or higher. And then you'll get an answer. Maybe ugly, but you'll get an answer. Now, graphing it, we're just going to go right here and do that. Now, technically, I know that -3, 1 is like right here. So if you really want to be technical about it, but it's shooting off in that direction. Basically, it's a quadratic on its side, and we're only looking at half of it. You should be able to visualize the rest of the quadratic right there. But that quadratic's cut off because of the domain restriction. Okay, next slide. For the function x² - 6, use the graph to find the function values. Sorry. Hide that. Is it on yours? It is on yours. Okay, never mind. I'll leave it there. Okay, so if I gave you the graph, imagine the helpful arrows were not here. Like, imagine you just had the curve. If I gave you the graph, x² - 6, zoom 6, here it is, and I said evaluate f of -3. Well, -3 on the x-axis is here, so where does it touch the graph? Like somewhere around here, correct? I can't actually pinpoint the value here. I'd have to go to the table and look at it. What's the other one? +1. So here's +1, and it touches the graph about here. Do you see that? Now look at your paper, where I've put the graph on your paper, and I've given you the helpful hints that if you were to read f of -3, it would land you here, which is what y-coordinate? +3. If you were to read f of 1, it would land you here, which is what y-coordinate? -5. So the purpose of this slide was, can you read a function value from the graph? I know you can just plug it in. That's a lot easier. But if I was to just give you the graph and I did not give you this at all, you would have to rely on the graph, right? That's going to happen in the homework. One of the homework problems is they don't give you the equation. They just say, hey, here's the graph. And you need to be able to read the y-coordinate from the x-coordinate they're telling you to evaluate. By the way, the graph is legible. There's no like, I'm not really sure if it's, a half or it's a whole number. It's easy to read. That's the point of this slide right here. Is what if I didn't give you the equation and I only gave you the graph and I asked you to evaluate numbers? What do you think?
Seems easy enough.
All right, we have 8 slides left. Go to, and we have an hour. We're doing good. Go to this slide. remember when we were talking about at the very beginning, I think it was last Thursday, if you had a set of numbers to determine if they're a function or not, you're checking the x-coordinate. If the x-coordinate repeated, we said it's not a function.
Yes.
Okay. What if I didn't give you the numbers? What if I gave you the graph? Enter the vertical line test. This should ring a bell. The vertical line test is a fast visual way to look at a graph and know if an x value repeats or not. So basically you visualize in your head dropping a vertical line anywhere on the graph, anywhere, and confirming whether or not it touches the graph in more than one spot. So I definitely am not interested in dropping a vertical here because I know it's only going to touch once. You need to go to where there's a lot of activity and see, is it going to touch in more than one spot? And that one clearly violates it 3 times, right? So by dropping that vertical line and confirming that it fails the vertical line test, this means draw an arrow to mean like, so that means not a function. It translates to repeated x values. That's what it translates to. If I sat down and wrote the coordinate points for that graph, there would be some x values repeated. Okay, so next slide. Real quick slide here. Ignore the stop button. That was I need to delete that. Look at all of these graphs and tell me if they pass the vertical line test or not. So on your paper, just write a yes or no, or a Y or an N to confirm that they pass the vertical line test. Are they a function? Okay, what'd you get for A?
Yes.
Yes? B?
No.
Definitely not. C? With confidence.
No.
Thank you. I was wondering. D?
No.
Thank you. E?
Yes.
F?
No. Yes.
Yes, because the bottom part is an open dot and the top is a closed dot. That means the bottom open dot is not included in the graph.
I'm going to let you digest what he just said, and I want you to rebuttal.
It says it in the instructions.
It's okay. But this is the trick. F is tricky because if you notice at first you might think, oh yeah, it's fine. The problem is this is closed on your paper. I want you to dramatically emphasize these circles. This one's closed. This is clearly open. So if I do drop a vertical line right there, then I'm not necessarily violating the vertical line test. So yes, this would be a function. Now it's that just go with it. My if I tweaked this by closing that circle in, it's no longer a function. So it all boils down to this simple, meticulous detail that is open. So you might think, well, why do they put that there if it's not including it? Well, they need you to know that it's going all the way up to as close as you can get to it without actually including it. All right. Which brings us to this. This is everybody's favorite. This is why I didn't want to stop yet, because we're making good time, and this is the hardest stuff for some people to learn, so I want to make sure
Can I take
we
a water
give
break
it
first?
full attention. What?
Can we take like a 2-minute break?
You want a brain break?
Yeah, I want a break.
Brain break.
I need a
Do you want me to play
Fall
the
asleep.
brain break dance moves? In terms of looking at a function and being able to say what the domain and the range are, you have to start training yourself to look for what's allowed to be plugged in, what's not allowed to be plugged in, what are the rules in math, and then once you can wrap your mind around what the rules are in math, basic rules that you already know, then domain and range is a lot easier. So let's look at this one right here. I'm going to start small. It says, first find the indicated function values if possible, then determine whether those values are in the domain of the function. So number one, or part A, is saying evaluate f of 1 and f of 3 in here. So do that now. And then we'll talk about what you get. You're evaluating f of 1 and f of 3. Evaluating means plugging it in, right? What did you get when you plugged 1 in? You got
Negative 1.
So when you plug 1 in, if you need to see it, it would look like that, right?
Right.
But then that simplifies to negative 1/2, right? Yeah. Doesn't matter where you put the negative. The negative is on the bottom. You'll notice I never put negatives on the bottom. It feels weird to do that. I always put it out in front of the fraction. Same thing. What happens when you plug the 3 in? On the bottom, you end up with 0, and if you remember what we've talked about,
No.
that's a no-go, right? That's a problem, which means undefined. Now the question said, evaluate the function and then determine whether the given values are in the domain of the function. Well, if you plug a number in and you get an answer, that means it's in the domain, okay? If you plug a number in and you get an error, it's not in the domain. So in this case, x equals 1 is in, I left off the word in, is in the domain. X equals 3 is not. Because when we plugged it in, we got an error. Because you can't divide by 0. Now do B. What'd you get when you plugged 16 in? You get 9? When you get when you plug -7 in, what do you get? You get undefined. Undefined is the more appropriate way to say doesn't exist. Because technically, it does exist, it's just crossing into imaginary. So undefined in terms of, yeah, I guess. So undefined is like saying, in terms of real numbers, it's undefined. If you plug -7 in, the square root of -7 from the get-go is a problem. You cannot do that. So in terms of what's in the domain, x equals 16 is in the domain. And x equals -7 is not. Because it gave me an error when I plugged it in. Now, if domain and range were as simple as that, that'd be great. This was mainly algebra. And you get an error, then it means no, it's not in the domain. We need to be able to get to the point where we can look at the function and state the domain for all numbers, okay? Which is the goal, which takes us to the next slide. Very good. Can I change it?
Domain is like a little fancy thing with X, Y, X.
It kind of goes back to that set theory where we were saying, which is why I put that in the Algebra 2 review, because it was coming up the very next week. So we already, touched on domain in the Algebra 2 review. The range is the same concept, but it's the y coordinates. So looking at this right here, we have 4 practice problems. And this may not even fit on your, let's see, how much room we got? Okay, y'all's is bigger than mine. All right, so I'm going to go back to this slide because I don't have a lot of room after we show all of our work for the next slide. There's not going to be much writing room. So I'm going to go back to this slide, change colors. So in between the 2 slides, or wherever you have space, like at the bottom of this slide, you want to ask yourself, spell it right, where are the restrictions? Where are the restrictions? What are the rules in math that I cannot violate? Well, one of the rules in math is you cannot divide by 0. Third time I've done that. Cannot divide by 0, right? I'm tripping over the room. You're welcome. That's so I'll stop tripping over the room. So in A, we learned that 3 was not in the domain because it generated a 0 in the bottom. That's a big no-no. You cannot divide by 0. In B, we worked with the square root of x, and we learned that you cannot take the square root of a negative number, right? So that was the restriction here. Moving to the next slide. What is this function? It's a giant, starts with an F, it's not 4 letters. It's a giant, yes, can you say that louder? This is a giant fraction. What's the rule with fractions in math? Can't have 0 on the bottom. So you would make a note to yourself, denominator cannot equal 0. That's the rule in math. That's going to guide you to the domain. What is B? B is a giant fraction. What's the rule? Denominator cannot equal 0. Right? Okay. C. That's a cubic and then absolute value. Are there any rules with those? Is there a number off limits of being plugged in? Can you think of an example, like a counter example? Like, oh, if I plugged in, -6, I'd have a problem. Oh, you can cube -6, and you can take the absolute value of -6, right? So does anything look off limits here? No? We'll dive into it when we get there. What about this one?
1.
What's the trick here?
It's cube root.
Cube root. It's not square root. So this one's going to have a little bit of a, think deeper about it when we get there. Is there any rules for cube rooting? No, you can cube root any number, right? May not be pretty. Can you cube root positives? Yes. Can you cube root negatives? Yes. Can you square root negatives? No. That's a rule, right? All right. So what we've just done is kind of glanced at them quickly and said what rule they would possibly break. Now we're going to actually dive in and state the domain. Once you realize what rule could be broken here, it's going to lead you to the domain. So example A, we said the denominator cannot be 0. So take the denominator, set it equal to 0, find what makes it 0, and then that number is off limits. Right? So we're going to take the denominator, set it equal to 0, and solve, and therefore x cannot be 7. That should look familiar from our Chapter R exam review. I went ahead and touched on this for that exam review because I knew it was coming up. But now we're taking it a step further. You've just stated, okay, x cannot be 7, but in order to state the domain, you have to tell me what is allowed. Well, I want you to visualize a number line where any number is allowed except for what again?
7.
So that would mean an open circle on 7, right? And everywhere else is shaded?
All the numbers are x is equal to 7.
Yes. And I'm going to show you interval notation because it's a lot easier to write in interval notation. So you could say the set notation from Algebra 2 review is that it's any x value, my R, hold on, let me fix that, from the real numbers except 7. That's the way we wrote it for the Algebra 2 review, Chapter R. Now I'm going to show you the interval notation using unions, and it's a lot easier. The way that you get it is you visualize a number line completely shaded with an open circle on 7. You always read number lines the same way you read a book, from left to right. Okay, and on the far left is negative infinity, and on the far right is positive infinity. So watch how I write this interval notation. We'll make a note. Or. Here we go. Domain. Left to right. I can use any number from negative infinity up to 7. Open on 7. Or, remember in our Chapter R notes, we learned that union means or. I can go from 7 to infinity and beyond. So write it down, and then I'm going to read it again so that if you can wrap your mind around it. And you might be thinking, how is that easier than writing the set theory? It just is. It shows you exactly what number, it also shows you where the shading is if you were to shade a number line. So here's how you read it. I can plug in any number from negative infinity up to 7, don't include 7, so parentheses. Union means or, so if you need to, remind yourself, union means or, from 7 to positive infinity. Again, you never put a bracket on infinities, ever, because you can't touch them. They're just directions. They're not destinations. So this is the way that I want you to start writing your domain, okay? Instead of saying what's off limits, I now want you to write what's allowed. See the difference between the two? This is saying plug anything but 7. This is saying, okay, you can pick any number from this direction or you can pick any number from that direction, but don't put 7 in there. Because if you throw 7 in, you get a problem. Right, Houston?
Yes, ma'am.
All right. If you look at B, B is another fraction, but it's obviously a little more complicated because the top is not a 1. The top is a polynomial expression. I need you to know there's 2 ways to approach B. One way is to factor the top, factor the bottom, look at what factors. Anything that cancels is a whole. We talked about that. And it goes in the domain, and anything left is an asymptote, and it goes in the domain, right? You can do that. Do you need to do it that way? No, not necessarily. If you just look at the bottom, if there is a whole that would cancel, won't it be in the bottom from the beginning before you cancel it? So you could just focus on the bottom, work with it, and then anything you come to in the bottom is off limits. Whether it's a whole or an asymptote. Doesn't matter, we're not graphing them yet. Right now it's just a matter of saying, can't plug this or this in. Does that make sense? So, for now, when I say the top does not matter, I only mean because we're not graphing. We're not graphing yet. When we get to graphing is when I'll say, now the top matters. So, I want to make a note. For now, ... top doesn't, I've run out of room. Shoot. I can't do it. Oh, that looks terrible. Doesn't matter. Top doesn't matter. It's the denominator equaling 0 that we need to focus on. So let's pull the denominator. Set it equal to 0. You can see where that algebra 2 stuff is coming in. We need to factor this. We need to solve this equation in order to see what values are off limits. Remember what I said to always treat A, whether it's 1 or not, as important. So then that way when it is not 1, you won't miss that step. So 1 times -3 is -3. Factors of -3 that add up to 2. 3 and -1, and since A is 1, will anything reduce? No. So when we go to our parentheses and do that shortcut of AX, we said 3, and AX, and we said -1, because A was 1, they're done in terms of factoring. Now we have the 0 product property. This crap times this crap equals 0, so we set each of them equal to 0, and we solve. And now what you've just done is solve the denominator for the values that would make it 0, which means these are off limits. Right? Now write it, or think of it in terms of a number line where the entire number line is shaded except for those values. So how many shaded sections do I have?
3.
I have 3, which means how many interval notations will I have? 3. Which is also why drawing the little number line is helpful, because then you can see exactly how many intervals you need to write. Now read it like a book. This is -infinity. This is positive infinity. We're going to write the domain. And I'm going to run out of room. But I'm going to do the best I can. So, coming from left to right, I'm going to go from -infinity up to -3. Union. -3 to 1.
Another union.
Yeah, another union, and this Y'all have no idea. That is going to give me nightmares. Just run out of room.
Can you like take it?
Move
as
it
you
down.
go, or-
I'm going to. It's
or
just.
downsize
Just
it?
give me a minute. Just give me a minute. This is. My OCD. Like I'm twitching over here. Can't stand this. All right, and then we go 1 to infinity, right? I can't do that. I gotta rewrite it. Hold on. Y'all have no idea. Like I probably should be on this. All right, I gotta fix that.
I'm gonna fix it by putting it over here. Here we go. Now I got to put it in.
Y'all laugh.
It wasn't you.
That's what he said. All right, negative infinity up to -3, -3 up to 1, and then 1 to infinity. Does it make sense?
Yes.
Union is saying, I'm not done, there's more.
It wasn't you.
You have to put the union. Union is saying there is more than just this interval that is allowed. There's also this interval or this interval. Union's important. And don't put intersection because intersection means it would have to overlap and there's no overlapping. Right? Alright, going to C. What did we say about C when we were kind of brainstorming? Could we come up with a number that, you know, if we plugged it in would give us an error? Do what?
Can you put y equals on your calculator and have a little this is error?
You could type that in the calculator, but in terms of, does it break any fraction rules?
No.
No, there's no fraction. Does it break the rule of taking the square root of a negative?
No.
No. Those are the only 2 rules. Can't divide by 0, can't take the square root of a negative. So if I was to try and graph this in my calculator, it would cover any given number you want to plug in. How do we write that? There it is. So if you visualize a number line, if you need the number line to visualize it, basically any number is fair game. So the domain is negative infinity to positive infinity. It might help to make a note. There are no restrictions with cubic or absolute value functions. There's no restrictions with a cubic. There's no restrictions with an absolute value function. You can plug anything in there that you want, and it's fair game. My number line is crooked, so. I got it.
Is it straight now?
It's alright, I'm starting to sweat. I've been OCD for perfection like all my life, so now I just make fun of it. It's part of my therapy, you know. Just make fun of myself. Alright, we're gonna squeeze in an extra practice problem before we get to part D. We're gonna squeeze it in right here. We're gonna say, I know. We're gonna say, what?
That's what she said.
I was waiting for you to say that, Brody. That's why it's so quiet.
Moving on. There's no way to go around everybody.
Solid.
All right. Let's create a new example. We're going to call it C1. Like,
Whoa.
or C2. C2. There you go. C2. Let's do h of x equals Stop.
Be careful.
I know. Do what I did. So in my notes,
That was perfect. That was amazing.
so in my college notes, if I need to go back and like put notes in a spot where there's no room, I put a sticky note over it, and then it's like a window that I can. Yes.
Huh?
No, you're.
What did you say?
Hey, what's so wrong with that?
I should say this class.
No worries.
Where's your favorite? I even pop my bag.
Oh, it's all always.
Hey, don't say it.
She hates soccer.
I don't hate sophomores.
Well,
You
you
have
teach them.
freshmen this year?
No. I flat out said, like, please don't give me.
Hey, you're recording.
I know, I love everybody.
It's a free second.
Actually, that's not true. I just hate everybody equally. There we go. It's fair.
You gotta remember this is all recording, Miss Holcombe.
I know.
Okay.
No, I don't hate anybody. Like, I get annoyed with laziness, and that's very common in underclassmen. You know what I mean? That's what I have trouble with that. I can handle you're not good at math. I can't handle you won't work. Like, I just want to.
Somebody else.
None of that was on video, by the way, so we're good.
Okay.
All right, so we have the square root of x plus 2. So in general, you ask yourself, what's the rule in math here? Can't take the square root of a negative number. So if you want, you could make a note to yourself, can't square root negative numbers. You want to make a note. That's where you're guiding yourself to say what the domain is. So if you think to yourself, I cannot square root negative, then that should set you up to say, but I can square root positive or the number 0. So the way that you approach even root functions, notice I said even, because what if it was fourth root? You can't fourth root a negative either. So the way to approach an even root function is to set the radicand greater than or equal to 0 and solve. And that's your domain. You're saying the radicand has to stay at 0 or above 0 by setting it up like that. So it's a little different than denominator can't equal 0, right? We set it equal to 0 to find out what's off limits. Here we're saying I need the radicand to stay at 0 or positive. So I'm going to set the radicand greater than or equal to 0 and solve, which requires me to subtract the 2. And that's your domain. You don't have to tweak it or anything. That's it. This is saying you can plug any number in as long as it's -2 or bigger than -2. So now visualize that on a number line. That would be a closed circle shaded to what direction?
Positive infinity.
Positive infinity.
That's the domain.
And that's your domain. It would be a bracket on -2, comma, to infinity and beyond. And I did my best, and it did fit right there on the screen. Everything looks good. Add on the screen.
I didn't say anything.
You did look well.
I want to write the sound again.
Challenge accepted.
That was the silence.
You're fine, you're fine. All right, let's go back now and finish this slide by going to D. D is not a square root, it's a what? Cube. A cube root. Well, can we take a cube root of positive numbers? Yes. Can we take a cube root of 0? Yes. Can we take the cube root of negative numbers? Yes, that might be ugly, right? Negative, even if it's positive, it might be an ugly decimal. But it is allowed. So what's the domain here? Yeah, all real numbers are allowed here. So the domain, and you don't have to draw that number line with the whole thing shaded. I'm just trying to help you see that there's not a single number off limits. And you might want to make a note. There are no restrictions with odd roots. And that's because the odd root of any number is evaluable? No. Evaluable? How do you say can be evaluated without having to use multiple words?
Evaluatable sounds wrong.
It does.
Able to be evaluated.
Just cut game.
Well, it's a fucking word.
Computable. No.
Evaluate.
I think it's able to be
Not value.
I was about to say, that show couldn't give you a good answer.
Wait, what?
You
say the same thing.
Odd root.
I slept. And watched shows.
We also have really good valuable. They're able to be
No,
evaluated.
Nothing's off the chapters about, and then we start talking about something like, oh, good. I've never read the chapters.
All right.
Yeah, he made us the other way.
What do you think? What do you think?
That was pretty.
A lot of red.
Oh, it was a one-time.
Now, when I turn you loose and you practice it, you're probably like, Miss Holcombe, I got it when you explained it, and then now I don't get it. And I'll be honest, that just means you need to practice it, okay? You've got to start somewhere and then try to work with how you're doing
Miss Holcombe.
at that point.
The one you made us write is right there.
Somewhere.
You made us write that one. Miss Holcombe. Oh my gosh.
I forgot last year I fixed it. So just take the sticky note and put it on that square. And then if you didn't put your work on a sticky note,
Oh,
You didn't say
the
that.
whole class.
sorry about your luck.
Hey, got it on recording.
I'm sorry. Anyways, you know what? I guarantee it. Like right now, go to this slide and try it without looking back at your notes. Oh. Oh, just like there's a billy goat in here. Nope, not gonna do it. Wouldn't be pretty.
Dude, don't say that, because how can stick for the rest of the
Hallie the Billy Goat.